Hey guys, welcome back. So we're going to be talking about complex ion solubility now. One of the things that we're going to be talking about is an acid-base example of the common ion effect, so that we can take a look at what happens there. I'm going to go ahead and share my screen so that we can get back into this set of slides. So we left off here, and we were getting ready to talk about the effect of acetate on acetic acid equilibrium. Now, acetic acid is a weak acid, so we have CH3 COOH going to H plus CH3 COO minus. Okay, that's awesome. Sodium acetate is a strong electrolyte, and it completely dissociates when it goes into solution. So NaCH3 COO goes to Na plus CH3 COO minus. Now notice, those are the same ions. So we're getting acetate from both of them. That means we have a common ion effect when we add that to the acetic acid. Now, the presence of the acetate from sodium acetate in an acetic acid solution will shift the equilibrium. So it shifts backwards because we've added this CH3COO minus, so we have to shift backwards to be able to compensate for that, okay? So that's the Chatelier's principle and how we see that in this effect. Now, practically, what is that going to look like? Let's talk about that. So what is the pH of a solution made by adding 0.3 mole of acetic acid and 0.3 mole of sodium acetate to enough water to make 1 liter of solution? So we're looking at the same equilibrium. We have that CH3 COOH aqueous coming apart to give me H plus and CH3 COO minus. I know that the Ka for that, and I'll write it over here because it looks better when we do, is H plus times that CH3COO minus over the HCH3COO, which is another way that I've just rearranged the letters, so please don't freak out. So I put the H on the other end. I apologize. We can do that. And that has a value that's given to us of 1.8 times 10 to the minus fifth. So when we set this up for our rice table, we have that equilibrium right here. We know that initially we have 0.3 moles of acetic acid, so that goes in this first column. We don't have any H that we're talking about initially, but we do have 0.3 moles of the acetate, so that goes in there as well. We know that our change is still to break down this acid to make the H plus and the CH3COO minus. And just a note for you guys, just in case you haven't noticed this. Whenever I set these rice tables up, whatever I have as my reactant is negative, and whatever I have as product is positive. Now, that may not always be the case. If that happens and I've set it up wrong, then the X value that I end up with is negative. All that means is that it should have gone the other direction. That's all it means. Okay? I know that comes out, it feels really weird to me when that happens and it comes out negative, but that's all that means. Okay, so I always set them up this way. So my change is negative X for the acetic acid. I get, and that should be a plus X and a plus X. So the H plus and the CH3COO minus are equal to each other. They're both X. That's what I should get. Now, I have values that I put down here in the equilibrium. That's based on the setup over here. So I took that 1.8 times 10 to the minus fifth, and I set that equal to the X times the X over, nope, and it's not an X and an X. I apologize. Give me 2 seconds. Doesn't want to erase what I wrote. So that 1.8 times 10 to the minus fifth is going to be equal to X times the 0.30, so that's my acetate ion, times the, yeah, okay, no, hold on. Yes, so those two, and then we have the 0.30 down here. Now, it's 1 liter of solution, so even though this is just moles, we know that if we do the conversion to molarity, it is the same. Make sure you understand that, because if your volume is not 1 liter, then we need to make sure that the calculations are done in molarity, moles per liter. It does not work if you don't, okay? So we set that over here. I know that 1 on top, 1 on the bottom, that goes away, and that means that my x value is 1.8 times 10 to the minus 5th. Awesome. That's really cool. And of course, that value is my x, which is my h plus, and that's how I get the pH is equal to the negative log of the h plus, which is 4.74. Now, we saw this before in lecture 3. We talked about using the Henderson-Hasselbalch equation. Again, it doesn't look great on this. So pKa plus the log of the CH3COO minus over the CH3COOH. And of course, since both of those are equal, that means we're going to take the negative log of the Ka, the 1.8, times 10 to the minus 5th, plus the log of 0.30 over 0.30. That term is 0, so it goes away, and that means that the pH is equal to the pKa. Okay, so pH equals pKa when we have an ideal buffer. So when that CH3COO minus is equal to the CH3COOH. Okay, so there is that. Now, just one other note I'm going to go ahead and make at this point. I had some questions in my physical class today, and based on those questions, I want to make sure that I talk about something. So you'll see me write occasionally HA going to H plus plus A minus. When I do this, this is a generic acid. So any acid that I have, I don't care what that acid is, it has an H, and then it has an anion that it's associated with. So it could be a Cl, it could be an I, it could be a PO43 minus. It doesn't really matter. There's something else there that is negatively charged. We call that, and since it's negatively charged, it's called an anion, and therefore we represent it as A. All behavior stems from this H plus and the anion. And so we represent them as H plus and the anion, which we have as a negative charge because it is a negative charge and because we know that it needs to be. Okay, so this is a generic acid. So I am not referring to any specific acid when I write this. This could be anything. So CH3COOH could be my HA, which would then make my A minus CH3COO minus. It could be formic acid. It doesn't matter, okay? The only thing I do know, based on the way that I've drawn those arrows, is that this is a weak acid, okay? So HF would work. And that would give me H plus F minus. However, there is a difference. When I talk about a strong acid, like HCl, you may have noticed that I go like this. Strong acids do not reassociate to make HCl. They stay as H plus and Cl minus. They're completely dissociated. That means that the K for this is going to be, it would be H plus times the Cl minus over the concentration of the HCl, but that HCl is 0, and that makes this mathematically undefined. So strong acids and strong bases do not have K values, and that's because there's none of that species left. All right, that equilibrium lies all the way over. So what you'll see there is that there's only one arrow, and it's only going in the right-hand direction towards products. And so that's what that means. Do I expect you to know to do that? Not necessarily, no. But there is significance in that when I write it. So when I have the double-headed arrows that I'm using on the left-hand side of the screen, that's because I know that that's a weak acid and I have both species present. Okay? But my point here is that all of these acids have an H. So the H that comes off, this is the H, this is the H, this is the H, and then something left. And whatever's, once you take that one H plus off, whatever's left is that anion. And that's what we're talking about when we talk about that A minus. So I use them interchangeably. You'll see that from time to time. That is not meant to confuse you. It's just meant that that's a generic one and we're replacing it with a specific. Okay, so that's all it's meant to be. And I hope that that's not confusing. All right. So that was our acid-base example. Go awesome. Let's talk about adding 0.238 molar NaF to 0.10 molar HF. Okay, so where do I start with this? Well, I'm interested in what happens to the HF because the HF is the acid. So it's the species that I'm looking at. NaF, on the other hand, is an ionic compound. It is completely soluble. So Na plus F minus. That is not interesting chemistry to me because it's all that direction. So whatever this concentration was, this is also 0.238, and this is 0.238. And of course, they're equal to each other and to the initial because it's a 1-to-1 ratio. So I have one of those NaFs coming apart to give me one Na plus and one F minus. So I know that. That's not interesting chemistry. The HF, on the other hand, is a weak acid. So we need to see what effect this ion is going to have on that weak acid. So I take my weak acid and I write that as falling apart to H plus the F minus. That's my R. My initial conditions, I have 0.10 molar HF. Awesome. I also have 0.238 molar F minus. We assume that the H plus is 0 initially. I still have the same change. Okay, so it's going to be a minus X here, plus X here, and a plus X here. At equilibrium, based on the table that I have 0.10 minus X. And all I'm doing when I get this equilibrium row that I'm looking at here is to add the two rows above it. That's it. So H plus is going to give me an X. F minus is going to be 0.238 plus X. We make the assumption that X is small compared to the 0.1 and compared to the 0.238. So when we do the calculations, we ignore it. Okay. So I take my Ka, that's equal to H plus times F minus over HF. And they start to sound like Eeyore when I say that because I say it over and over and over for the Ks. I get a little tired of it. So, but that's what that looks like. I know that this has a particular value. I take my exam handouts and I look to see what that value is. And I see that HF is 7.1 times 10 to the minus 4th. That's a 4, I swear. Okay. My H is an X. So 7.1 times 10 to the minus 4th. So I pulled that 7.1 over to this side. And I'm making that equal to the H plus concentration, which at equilibrium is X. My F minus concentration, which at equilibrium is 0.238 because we ignore the plus X. And the equilibrium concentration of the HF, which is 0.10. I need to solve for that X. So my 7.1 times 10 to the minus 4th gets multiplied by 1.10 when we pull that over, and then divide both sides by 238. So again, I'm going to multiply by 0.10 there. And that, since I've multiplied and divided both sides by that, that's going to leave me with an X. Yay, that's awesome. I can calculate that, can't I? Well, I hope that I can. If my calculator will work with me. 7.1 second EE negative 4 times 0.10 divided by 0.238. And that gives me X is equal to 2.98 times 10 to the minus 4th. That is my H plus. So if I needed to get a pH, the negative log of that number, pH, is equal to that. So negative log of that happy answer would give me 3.52. Okay. So the presence of that F minus, the very fact that it's there, means that I am not as able to dissolve HF. So this equilibrium pushes back in that direction. And so that HF doesn't come apart as much. Since it's not coming apart, that means that that H plus concentration is very small because it only comes from the dissolving of HF. That F minus we have from somewhere else. Okay, so that's what we're seeing, is that H plus is less soluble because of the presence of the common ion. Okay? Awesome. Let's try it again. And so we're going to add a 0.623 molar NH4Cl to 0.025 molar NH3. Now, NH3 is not an ionic compound. It is a nonmetal to nonmetal bond. That means that it is a covalent compound. That means it does not come apart. So that's not what I'm looking at right here. Okay? The NH4Cl is an ionic compound. It comes apart to give you an NH4 plus ACl minus. Whatever this concentration was, 0.0623 is going to be 0.0623, and this is going to be 0.0623. So that carries directly over, and actually this should not be like that. That should be like that, because it only goes that direction. Okay, so we don't go backwards once we get them into solution. Okay, completely dissolves. So that gives us our concentration for the NH4 plus. Now, if I'm looking to study the NH3, it reacts with H2O. So NH3 is a base. It reacts with H2O. When it does so, it abstracts a proton and becomes NH4 plus. And that leaves me with an OH minus from the water, because all I have left of the water is the OH minus because I took one of those protons. Okay, fine. So that's the reaction that I'm looking at there. My weak bases always react with H2O to do this. We can sort of kind of talk about the acids doing the same thing, but it's not necessary because we assume that H3O plus and H plus are exactly the same, which, I mean, really they are. So it's just the way that we talk about them that's different. I know that my initial concentration of the 0.0623, or sorry, of the NH3 is 0.025, because that's what it says. I also know that I have an initial concentration of the NH4 plus, which is 0.0623. Okay, this is a liquid, so I don't care about that. And the OH minus we're assuming to be 0. Now, when this comes apart, I get a negative x, I get a plus x there, and a plus x there. So adding those two together, I get a 0.025 minus x. We ignore the x because it's small compared to the initial concentration that I have. The NH4 plus, we would have a 0.0623 plus x, but again, we ignore the x there, and that leaves us with our OH minus being equal to x. The Kb for this is going to be the NH4 plus times the OH minus over the NH3. I have an NH4 plus of 0.623, 0.0, sorry, miswrote it, 0.0623. My OH minus is an X. My NH3 is a 0.025. And I have to look up the Kb for NH3, it being weak base. I can find that in my exam handouts. And my ammonia is listed as 1.8 times 10 to the minus fifth. So 1.8 times 10 to the minus fifth. We'll end up multiplying by 0.025. We'll end up dividing by 0.02623, and that's equal to x. Okay, so I've moved everything to the other side except for the x. I've isolated x on its own. So 1.8, second e negative fifth times 0.025 divided by 0.0623. And that gives me an x equal to 7.22 times 10 to the minus 6th. And of course, if I, and what is that? That's the OH minus concentration. So I could put that right here. I can also take POH is equal to the negative log of that value. So if I needed a POH, I could get it. And that gives me 5.14. And so if I need a pH, that'd be 14 minus the 5.14. And that gives me 8.86, which makes sense to me. It's a basic solution, so I would expect it to have a high pH. Okay, so that's what I've been asked to do. And I have solved for what is the concentration of the OH minus? How does it change that having both of those things there? Now, one other thing I need to bring to your attention when we're looking at all of these examples we've been talking about, we've been talking about weak acid and its conjugate base, or weak base and its conjugate acid. These are buffers. Okay, buffers resist changes in pH because the acid can react with any base that's added. The base can react with any acid that's added. So there is a finite ability to do that, but it is a buffer. So we need to treat it as such. This being a weak base with its conjugate acid, same is true here. So that weak base can react with any acids that we add to it, and that NH4Cl can react with any bases that we add to this. Okay, so those are buffer situations. One thing that I will mention to you is we need to know ways that we can make buffers. So there are two major ways that we make our buffers. One is by taking and adding the conjugate acid to this weak base, or the conjugate base to a weak acid. So if I directly add them, that's I've now made a buffer and I've got a buffer. Go, awesome. The other way that we can do that is to take a weak base or a weak acid and titrate it with a strong acid or strong base. So the opposite thing. So if I take this NH3 and I titrate it with an HCl, if I don't go all the way, I have generated some NH4 plus and still have some NH3, so that's a buffer too. Okay, so both of those are ways that we can generate that. You need to be aware of both. Okay, let's see what else we've got. Let's try one more, because I would rather you fast forward through me doing this than you wanting more. So 0.025 molar NaCN and a 0.1 molar HCN. So HCN is an acid. That's the one I'm going to be interested in. The 0.025 molar NaCN is an ionic compound. I have a metal to polyatomic ion bond there. So when the NaCN comes apart to be an Na plus a Cn minus, this concentration is therefore this concentration is therefore this concentration. And if I'm looking at the HCN coming apart to give me an H plus a Cn minus, our initial conditions for our HCN is 0.1. This Cn minus is 0.025. The H plus is assumed to be 0. I know that my change is negative x for my HCN. I get a plus x and a plus x there. We add those rows together to get a 0.1 minus x. We ignore the x, and a 0.025 plus x. And again, we can ignore that because that number that's already there is large comparative to the x that we're going to find. We can't ignore it if I don't have a value, okay? Otherwise, we would have nothing to solve. And we're just trying to make the math easier. Really, the way that this should be set up is with all of those x's in it. We should have to go through the complicated math to figure this out, okay? But I'm not going to make you do that. It's not that different. I mean, statistically, it's not important. So there you go. Here's my situation. Now, I know that this is a weak acid, so it has a Ka, and I look in my exam handouts, and I see that my weak acid, HCN, hydrocyanic acid, is 4.9 times 10 to the minus 10th. And that is equal to the H plus concentration times the Cn minus, and that's really small and really squished, over the concentration of the HCN. Really small, really squished. Yay. I hope you can actually read that. So 4.9 times 10 to the minus 10th, plugging numbers in. We don't have an H plus, that's an X. So we plug that X in. My CN minus, I have, and that's 0.025. My HCN is 0.1. So now I can isolate that X, 4.9 times 10 to the minus 10th times 0.1 divided by 0.025, and that's equal to X. Sorry. And so I take my 4.9 times 10 to the minus 1, I multiply that by 0.1, and I divide that, wait, helps with my calculator as well, times 10 to the minus 1 times 0.1 divided by 0.025. Okay, awesome. That gives me, oh, that's not a 1, that's a 10. That would help a lot. So I'm going to look at my entry. I need to go back and insert 0. That should look better. Yes, that's much better. And I get that X is equal to 1.96 times 10 to the minus 9. Now, I hesitated when I did that calculation. I knew that I'd made a mistake. It said that the answer was 1.96, and that was huge comparative to what I was expecting. I was expecting a number that's less than 0.1 or 0.025, and that was not. So I knew that that didn't pass my smell test, and so I had to go back and review my work, and of course I had left off the 0 from the KA, so I needed to modify that calculation. And I think I actually had it, I just didn't see that it was there. So, there, because this should be the minus 10. And I just didn't see it when I did that. So that's my X value. That X value is the H plus. And I see that that H plus is way smaller than I would have expected it to be had there not been a common ion present. Yay, awesome. Every time I have a common ion present, things don't go as well as we would have expected. They're less soluble because of that presence. So again, having this thing here, this concentration being up, that drives this reaction backwards. And then HCN cannot dissolve as much as it used to. So since it can't dissolve, that H plus concentration is not very big. Okay? So that's what happens when we have a common ion in terms of acid-base reactions. Now, the next thing we're going to talk about is complex ion formation. I'm going to go ahead and stop and take a break here. So we'll come back in a couple of minutes. And hopefully you guys are okay with that. If you're not, please let me know. I want to hear from you. Tell me what's going on. Okay, thanks, guys.